Well, hello, welcome to MOS Live and happy Indigenous Peoples Day. You're joining us just in time for our coolest science story, where today we'll be talking all about the quantum revolution. We'll share some fun facts about quantum mechanics, and we'll have a chance to take some questions from you at the very end. Now, if you're joining us on Zoom, you can start entering your questions whenever you'd like by clicking the Q&A button on your screen. If you'd like captions, you can access those by clicking the closed caption button at the bottom of your screen and selecting Show Subtitles. If you're joining us on Facebook or YouTube, unfortunately, we cannot see your questions, but we're thrilled that you're tuning in. Now, let's get started. My name is Megan. I'll be one of your presenters today. My pronouns are she and her, and I am joined by a fabulous colleague who I would like to invite on to introduce herself.
Hi, my name is Meg. My pronouns are she and hers, and I'm really excited to share some fun things about quantum physics with you.
Great. We will hear more from Meg in just a little bit. But now let's jump into our presentation. Now, today, we are going to take a trip into the amazing and unexpected world of quantum mechanics. Now, quantum mechanics is the physics that describes the behavior of the tiniest building blocks in our universe. Things like atoms and the tiny particles that make up atoms, which are all way, way, way too small to see. And these tiny atoms and particles, they make up everything in our universe. Big things like stars and planets, living things like dogs and plants and people, non-living things like rocks or guitars, the air we breathe, everything. Which means that quantum mechanics describes how everything in our universe works at the most fundamental level. So let's dive into this quantum world. And in order to do that, first, we need to talk a little bit about energy. Electromagnetic energy, that is. Now, all objects absorb and emit energy in the form of electromagnetic radiation, which includes things like the visible light that we can see and the invisible heat or infrared light that our bodies give off. And this electromagnetic energy or light, it travels in waves. The wider waves at one end of the spectrum have less energy, and the thinner waves at the other end have more energy. And the width of the wave is called a wavelength. And for a really long time, this wave-like nature was the only way that scientists thought about light. But back in the early 1900s, some discoveries were made that changed everything.
Yeah, that's right. One of the most groundbreaking discoveries about light energy came from this guy, Albert Einstein. He discovered that light is not just a wave. In fact, it actually behaves also like a particle. A particle is called photons. So photons are little packets of light that carry a very specific amount of energy. And the amount of energy a photon has depends on its corresponding wavelength on the electromagnetic spectrum. For example, if we look at the visible part of the spectrum, a photon of blue or purple light has more energy than a photon of yellow or red light. Things that have a discrete amount of energy, like photons, are called quanta. One quantum is a quantum. One quanta is a quantum, as in quantum mechanics. And this discovery of quantized energy opened the door to even more discoveries.
Yeah, for example, this guy, a Danish physicist named Niels Bohr, back in the early 1900s, he was trying to figure out what in the world atoms are and how they work by studying their spectra. Now, if you've ever split light with a prism, you've probably seen the spectrum, all the colors of the rainbow that make up white light. Now, if you heat up gases of specific elements like neon, they give off light. So if you were to heat up a gas and shine the light that it emits through a prism, well, you'd see that it doesn't give off a whole spectrum like white light, just some of it, creating a series of bands. And each element or type of atom in the periodic table gives off a very unique pattern of colors. In fact, these spectral lines are so specific to each atom that you can use them like fingerprints to identify atoms and molecules. Astronomers use spectral analysis to figure out what stars and planets are made of. But no one had any idea why atoms give off their own unique spectra of light. Well, Bohr figured it out. Now, you might be familiar with this model of an atom. Well, it was Bohr who came up with this model. There's a nucleus at the center of the atom and electrons orbiting around. Now, Bohr said that atoms have different energy levels in which their electrons can exist. The electron can gain or lose energy, but it cannot be in between energy levels. Now, you can give an electron some energy and bump it up a level by shining a light on it. The electron can absorb a photon of light and gain energy. But the electron can only gain or lose very specific amounts of energy. The energy has to come in a packet of a certain size, a quantum. And because different colors of light have different amounts of energy, the electron can only absorb certain colors. If the wrong color of light comes along, well, it will have the wrong amount of energy, so the electron can't absorb the light. It has to have just the right amount of energy to be absorbed. So all the colors of light that can't be absorbed or emitted by the atom, well, we don't see them in the atom spectrum. All we see is that series of bands. So it turns out not just photons are quantized, but the amount of energy an electron can have is quantized too. So a whole bunch of scientists got together to try to figure out what all this meant at the Solvay Conference on Electrons and Photons back in 1927. And this was the beginning of the first quantum revolution. A new field of physics was born and a new era of discovery began. And one of the most important and mind-blowing discoveries of quantum physics is something called wave-particle duality. Now, remember how light acts like both a particle and a wave.
Yeah, well, the same is true for matter, stuff made of atoms. The particles in an atom, like electrons, also act as waves. But how is a particle like a wave? That's sort of like saying a ball acts like a wave. But what about a ball, like an object like that, is wavy? So let's go back to Bohr. In Bohr's model of the atom, electrons orbit around a nucleus. But this isn't quite right. Rather than the electrons orbiting the nucleus like a planet orbits the sun, the electron actually occupies a sort of a cloud around the nucleus. There's only a probability or chance that the electron will be in a given place at a given time. This probability defines the wave nature of particles. To explain, let's try an analogy on the human scale. Imagine you are arriving at the Museum of Science here in Boston. Now, when you first arrive, there is just no way for me to know where in the museum you are. You could be on any level at any exhibit, but maybe you have preferences. Perhaps there's a 30% chance you're in our Charles River Gallery, and there's a 10% chance you're in Wicked Spat, and there's a 60% chance that you're listening to me give a presentation on stage. And these probabilities can change over time, going up and down like a wave. Where you are more likely to be, the peak of the wave will be bigger, and where you're less likely to be, the peak will be smaller. And this is very similar to what we see on the quantum scale. So quantum particles, like electrons, are also waves, and that's because the wave is basically a map of the electron's existence. Where the peaks of the wave are bigger, that's where the electron is most likely to be. And where the wave is smaller, that's where the electron is less likely to be. But here's why the tiny quantum world differs from what we see on the human scale. Quantum particles actually exist as this wave of probability until you observe them. So going back to our human analogy, let's imagine that you are actually listening to me give a presentation on stage. That means I can see you. So I know there's 100% chance that you're right there. But even before I could see you with my own eyes, you were definitely somewhere, whether I could see you or not. But this is not actually true for quantum particles. On the quantum scale, it's not just that we don't quite know where a particle is, it's really not in any one place. There's only a chance it might be in a certain place or state until you observe it using scientific tools. As soon as you observe this particle, the wave collapses, and now it's just a particle in one very definite place. But when you're not looking, quantum particles like electrons exist as a wave of probability, a fuzzy cloud of chance around the nucleus. So, what does that mean? If there's just a chance that an electron might be somewhere, is it anywhere? It's sort of everywhere, all the locations or all possible states at once. To demonstrate, here we have a model of an electron, a quantum particle, and it can be in an up state or a down state. And actually, until we observe this particle, it's in fact up and down and anywhere in between, all at the same time. This is called quantum superposition. Mhm.
Yeah, so if I were a quantum particle, I could be in a superposition of sitting right here and sitting there behind me at the exact same time, which would actually be super creepy. So it's a good thing that I am not a quantum particle. But now, if you're thinking all of this quantum weirdness is a little hard to believe, well, you're not alone. There was one person in particular who was skeptical about some of the ideas of quantum mechanics: Einstein. Now, Einstein had come up with a theory that said that nothing can move faster than the speed of light. So there's got to be a limit to how fast things can move. For example, this dinosaur couldn't just instantly go from point A to point B. It has to travel through some amount of space to get there. But when Einstein dug into the mathematics of quantum mechanics, he and some fellow scientists revealed something that we now know as quantum entanglement. Now, entanglement is a mysterious link that can exist between quantum particles, which allows the entangled particles to affect each other instantaneously. Now, to demonstrate, let's pretend that these two glowing balls are two quantum particles, and they can be in a whole bunch of different states, which we'll represent by different colors. Now, right now, let's imagine that these particles are not entangled. They're just doing their own thing. Now, let's also imagine that these two particles are each in a superposition of all of these different states or colors, which we're representing by this blinking between those different colors. But remember, in a real superposition, the particle is not switching back and forth between states. It's literally in all possible states at the same time. Now, if we observe either of these particles, they will collapse out of this superposition into just one state. So if we observe just one of these two particles, just the one that we observe will fall out of superposition and be in just one single state or color, while the other is still doing its own thing in a superposition. But if we entangle these two particles, which scientists can do in a laboratory, and we set them up so that they are completely separate from each other, there's nothing connecting them at all. And again, we put each into a superposition of all those different colors. Well, now, if we observe just one of these two entangled particles, well, now both particles end up in just one state at the exact same time. And there's no delay between when these particles collapse out of that superposition. They both change at once, even though we only observed one of them. But the craziest thing about entanglement is that you could put these two entangled particles as far away from each other as possible, like at opposite ends of the whole entire universe, and they still can affect each other instantaneously. So it appears as if they are sending information to each other faster than the speed of light. And this was just too weird for Einstein to believe. He called quantum entanglement spooky action at a distance. Now, the existence of entanglement doesn't mean that any of Einstein's theories are wrong. Einstein just didn't understand entanglement yet, and he thought that it was impossible. But like we all are at some point in time, Einstein was wrong. Entanglement is real. And today, it's been supported experimentally time and time again, using everything from tiny diamond crystals to huge telescopes that capture light from the distant universe. But another reason that we know entanglement is real is because we've built technology that's based on it. Now, scientists have actually been able to use entangled photons to teleport information from Earth to outer space. In fact, all of these strange theories of quantum mechanics have held up so well that it's now called the most successful theory in all of science. And now we know quantum mechanics isn't weird or strange. It's really how nature works at these teeny tiny scales. And that brings us to today, where we're in the midst of a second quantum revolution, where new generations of physicists are figuring out how to control and harness the cool quantum behaviors like superposition and entanglement to create a brand new wave of quantum technologies. For example, that satellite that teleported information from Earth to space, it's the beginning of a new quantum communication system that can harness the power of entanglement to keep information safe from hackers. And one day, this technology could lead to a quantum internet that could be used to share valuable information safely from around the world.
Another example of quantum technology we could see in the future, and one that you might have heard about, is a quantum computer. These ultra powerful computers harness the energy of quantum properties of superposition and entanglement, which could one day allow quantum computers to do calculations that even the most powerful supercomputers that exist today can't handle. Scientists around the world at huge companies like Google and IBM are racing to see who can build the first one. So quantum computers won't replace our regular computers like laptops, but they could help us make big advances in areas like climate modeling, drug discovery, artificial intelligence. And they could also help scientists better understand how atoms and particles work, so we can discover even more about this amazing quantum world. So, over the last century, quantum mechanics has gone from a radical, debated new idea to an incredibly precise theory that describes the fundamental and unexpected nature of our universe. And it's now inspiring a new wave of innovation in science and technology. So, welcome to the new quantum revolution. And I'm now going to invite my co-host Megan to join me again, and we would be happy to take any of your questions. If you're joining us on Zoom, you can type them right into the Q&A box at the bottom of your screen. If you're joining us on Facebook or YouTube, I'm afraid we can't see your questions at this time, but we're really happy that you're here. And I'm just going to start off with a question for Megan. Uh, what do we mean when we say the quantum revolution, or revolutions, I should say?
Well, yeah, we just saw that there was a first quantum revolution and a second quantum revolution. And so the reason we call them revolutions is because of the extraordinary amount of change that all these discoveries about the quantum world brought about. And so when we talked about back in the early 1900s with Einstein and Bohr, um, these were really kind of groundbreaking discoveries because everyone thought about the way that light behaves as really being wave-like and continuous. So this idea that everything was kind of compartmentalized into photons or having to have a very specific amount of energy, um, these were ideas that no one understood. And so they really needed to dig in to see what it all meant. And once they started to make some discoveries, it kind of exploded into this new field that we call quantum mechanics or quantum physics. And so that was really this first quantum revolution where people discovered what quantum physics was. And then, gradually they started to be able to use that to create things like lasers. And eventually that led to pretty much all the types of electronic devices that we have. But the difference with the second quantum revolution is that now we're actually harnessing like these really interesting behaviors like superposition and entanglement, and being able to use individual atoms and particles to build new types of computers and new types of technology that is very different fundamentally from the type of technology that we have right now, and could help us do really amazing things like understand more about the world we live in and design new types of medicines and materials, be able to communicate securely. And so that's the kind of revolution that's coming about now. And so those are the types of technologies that we could see in the future that are based on quantum mechanics. So now I am going to ask a question of Meg. What do you see quantum computers working on in the future? What are the applications of quantum computers?
Yeah, that's a great question. So we put up a few examples earlier of particularly kinds of science research that involve lots of really intense modeling. So when we can't run an experiment in the physical world, for example, let's use climate modeling as an example. So we only have one Earth and we can observe what's going on with it. We can't really set it up in a physics lab and run lots of experiments over and over to see what happens when we change this or change that. Which you can do in some branches of science. So instead, scientists use computer models where they put together everything that they do know that we have determined from the laboratory or from other observations, and then try to run that forward and see what kinds of predictions we can make based on what we already know. And that kind of modeling takes a huge amount of computing power today. And there are lots of supercomputers that are used all over the world now that are trying to run lots and lots of simulations in order to make our best predictions about what to expect in the future. We expect that quantum computers are going to be able to help us with these kinds of modeling problems because the specific nature of those quantum properties that we were talking about using the principles of superposition and entanglement will allow calculations to go on simultaneously in a way that is just not possible with classical computers. So things that would normally take a super long time for a regular computer to calculate using sort of regular classical calculations will just take a much, much shorter time. And that'll help us with climate modeling. It'll help us with modeling things at the very tiniest scales, like actually understanding how atoms work themselves, and other things like artificial intelligence. Oh gosh, there's just a whole range of things that can really benefit from these kinds of intense models. So I thank you for that question. I have another one for Megan now. We saw the first quantum revolution and the second quantum revolution. Do you think there will be a third quantum revolution? And what will that be like?
Wow. So who knows? And I would like to think that maybe there will be. Once quantum computers are something that scientists are hard at work on right now, but we don't really have, a universal working quantum computer right now. There are some things called quantum simulators, things like that can do certain computations using quantum physics, but there's no universal quantum computer that just does all of the things that we dream of quantum computers doing yet. It's still something that's a little out in the future. Things like quantum communication that we talked about, where we can create these like unhackable communication networks using entangled particles. That may be something we'll see a little sooner in the future. People are, particularly China, is starting to actually set up these quantum communication networks, and we're making big steps towards being able to have that type of technology. But they're not things that we're using at a huge scale right now. So we don't actually know what could come of that or what more discoveries we could make once those types of things are really up and running. Science is going to keep going, and we're going to make more discoveries and figure out maybe other amazing uses and helpful problems that we can solve using the laws of quantum mechanics. And that could maybe one day down the road be the third quantum revolution, where we have something beyond quantum computing. Who knows? But maybe if you're interested, that's something that you can work on. And if you become a scientist, or you might be able to help us bring about the third quantum revolution. Who knows? Right now, that is completely an open question, and I am excited to find out if it happens. All right, well, I think we have time for maybe another question or two. Meg, I have a question for you. Are there any things about quantum mechanics that we can kind of notice on the human scale, or things that we're familiar with that are governed by quantum mechanics that we maybe don't realize? My
Yeah,
dog.
that is a good question. Yes, hi. So these kinds of what seem like strange behaviors at the quantum scale, like things being in a superposition of states or behaving like a particle and like a wave in different circumstances, are not things that we would normally expect to see on the human scale, which is why they seem so odd, and why, for example, Albert Einstein was so unconvinced by the idea that entanglement could be real. Um, but they actually do govern like basically everything from the ground up in our existence. So it is a super important aspect of our everyday lives that we just happen to never see because it's all happening at a scale that we just can't see. So there are certain examples that come to mind that of like sort of macroscopic or big scale effects based on these principles. One I think you mentioned just earlier is the laser is a good example of a technology that is built on the principles of quantum mechanics and is really only possible or made possible by sort of harnessing the quantum nature of photons to sort of have them all march in step with each other to produce that nice red or green laser pointer beam that we're also familiar with. And maybe we can use to torture to play with our cats. um, but for the most part, these effects are sort of beyond our perception, but they are there, they are fundamental, and they are very real no matter how strange they may seem. Let's see. I think we might have time for one more question. And I was sort of curious about that quantum communication system. And sort of, Megan, what do you see as the advantage of these sort of quantum technologies in the realm of like security, for example?
Yeah, that's a good question. And I think what scientists are sort of predicting with these quantum communication networks is that they would be sort of like an unhackable communication network, because what they can do is create basically like a secret code or a key for your information using entangled particles. And so they can use, say, for example, you had two photons that were entangled. And so they have this strong connection between each other. And scientists can actually use these entangled photons to create like to send signals. So these photons contain information and they can be sent along. And if someone were to come in and try to observe this signal that you're sending with these entangled photons, well, they're making an observation of those photons. And so they're going to change them. Say those photons are in a superposition, well, they would now collapse into a single state. And so by just observing, if a hacker came in and they were like, I'm going to look at your secret code, just by looking at it, they will change it. And so whoever is at the other end of this communication network, they would know that someone was looking and had changed these photons in some detectable way. And so they could say, okay, stop the signal. We're not sending this information because someone's trying to hack us. And so that's a very sort of simplified description of how these quantum communication networks would work, because they wouldn't just be based on our typical ways that we code information to try to keep people from being able to see sensitive information. They would literally be protected by the laws of nature, which are far more difficult to break into. So that's one way that they would be pretty useful in helping us keep information secure. That's a great question, but it looks like we are just about out of time. Thank you so much for joining us. And I'm going to give Meg a chance to say goodbye before we go.
Hi, everyone. Thanks for attending.
Thanks so much, Meg. All right. Well, thank you so much for all of your wonderful questions. We had so much fun with you today. And if you are interested in learning more about quantum physics, you can head over to Nano Nerds on YouTube, where we have a whole bunch of videos to check out. And we also have a lot more going on over at MOS at Home. So follow us on social media or check us out at www.mos.org/MOS at Home to see what we're up to. And if you enjoy our programming and would like to support the museum, please visit engage.mos.org/dino. To support us, your donation will help us continue to bring virtual science experiences to you at home and free of charge. All right, well, thank you again for joining us, and we will see you next time.